6.1 Basic Concepts of Hypothesis Testing. So in order to understand the hypothesis testing, we need to understand this accept-reject decision-making process, type 1 error and type 2 error. So I'm going to go over these during these slides. Let's look at the example which we have already, which we used before with the central limit theorem. So in our example, we have a machine which is cutting the silk material, and mu is equal to 1000 millimeter, and we have 36 sample. Therefore, our sample standard deviation is 2 millimeter. Say that we have the machine is cutting at about average 1000 millimeter. But if you cannot watch the machine every second. What happens if you leave the machine and then you came back and then you see you took a piece and it is about 996, 998? Are we gonna say that machine is not working properly? What are we gonna do then? Are we gonna throw the machine, or are we gonna call someone to look at it? What are we gonna do? We have to understand and we have to put some guidelines in order to understand if the machine is working properly or not. So first thing is the decision making. Accept, reject decision making, which is having the 3 steps. First step is to have an initial assumption. Initial assumption saying that we are suspecting that machine is working properly and cutting average of 1000 millimeter. And the second step is establishing some guidelines. We are using often in middle 95%. For the middle 95%, the last step is the decision. For the middle 95%, we are gonna say that machine is cutting properly in between, if we have a sample average, between 996.08 and 1003.92 millimeter. And then we are gonna accept that mu is equal to 1000 millimeter. But when we are doing this decision, we are going to adopt that middle 95% of the sample average values are accepted. But for the 5% of the time, we are going to reject. And in other words, there is a 5% probability of rejecting a properly operating machine, when in fact we should not reject it. So this is called type 1 error. And type 1 error is denoted by the symbol alpha, and which is called level of significance. Alpha is equal to, for this example, 0.05. So alpha is equal to 0.05, saying that we are having 5% of the time out of these ranges less than 996.08 and greater than 1003.92. What if we want to widen this range? What if we say that let's say that alpha is equal to 0.01? What's gonna happen then? So by opening up the range for accepting the machine as operating properly, we are gonna reduce the risk of a type 1 error from 5% to 1%. But this is gonna give us another risk. This is called type 2 error. And when we adopt the guideline of having the sample average between 994.84 and 1005.16 assumed to come from a properly operating machine, a machine is cutting okay at 1000 millimeter. So we accepted the machine is cutting 1000 at the 1000 millimeter. But what happens when we leave the machine and we see that the average is becoming 995 millimeter, shifted to 995 millimeter. A pin stuck in the machine or something happened to the machine. So in reality, the mu changed to 995 millimeter. So then we are just committing to type 2 error, accepting an initial assumption in error, saying that we have the machine is cutting 1000 millimeter, but in actuality it is shifted to 995 millimeter. So the probability of committing a type 2 error is denoted by symbol beta. So power is also another term. Statistician will often evaluate a statistical test in terms of its power. Probability of making a correct decision by avoiding a type 2 error is called power, and it is calculated by 1 minus beta. So let's look at some of the applications. Let's look at a couple of examples. First example is in the cutting machine problem. Suppose we establish the middle 92% of the sample averages as our cutoffs for accepting mu is equal to 1000 millimeter, assuming sample size is 36 and standard deviation is 12 millimeter. What's the probability of a type 1 error is the first question. So when you look at it, we are saying that middle 92% is the machine is cutting properly. Therefore, type 1 error is going to be 8%. Why? Because of when you subtract 92 from 100, you will get 8%. And we can say that in statistical form, alpha is equal to 0.08. So second part of the question is asking us between what sample average values would you accept the machine cutting at mu is equal to 1000 millimeter. So in order to find that, we are gonna look at the cutoff, at the critical cutoff values. So how are we gonna find that? We know that 92% of the time we are saying that machine is cutting properly, so we are looking at the middle 92% area, and we know that it is symmetric. Normal distribution is a normal distributed graph, so it's symmetric. So if we divide the 92 to 2, we are gonna get 46% is one area over here until the cutoff value, and 46% is the other area. So when we look at the z table, we can find the values for 46% or 0.46, which are 1.75 and negative 1.75. So z values for the cutoffs are negative 1.75 and positive 1.75. So we are going to work backward. We are going to use our z formula again. When we substitute negative 1.75 in our z formula, we are going to find our sample average value is 996.50. And when we substitute z is equal to positive 1.75, we will get the sample average value at the cutoff 1003.5. So let's look at another example. In the, again, cutting machine problem, suppose we arbitrarily establish sample average values 997 millimeter to 1003 millimeter as our cutoffs for accepting mu is equal to 1000 millimeter. Assuming the sample size is again 36 and standard deviation is 12 millimeter. What's the probability of a type 1 error? First question. So in order to find a type 1 error, we are gonna use our cutoff values, sample average values, in our z formula. Before doing that, we can calculate again the sample standard deviation. How? Sigma over square root of n. Earlier I didn't show it. It's the same thing for the example before this one, which is equal to 2 millimeter. And when we put the sample average values and our mu in our z formula, we get negative 1.5, and 1003 for the sample average over here, we get 1.5, which means that we are gonna have the when we calculate the area over here, how we are going to calculate the area over here, we are going to look at the z table. On the z table, you can see that when z is equal to 1.5, for you will see that 0.4332, which means 43.32% is this part. And what is left over here, less than this 997, is 6.68%. So we can say that the probability of type 1 error is 6.68 plus 6.68%, which is 13.36%, or alpha is equal to 0.13. So next part is what is the probability of a type 2 error if the machine shifts and is now cutting at mu is equal to 995 millimeter. So in order to find the type 2 error, we are gonna still use the same sample averages, 997 and 1003, but we are shifting our mu to 995. So we can use the using the 997, we got z is equal to 1, and using the sample average value 1003, we got z is equal to 4. But when you look at it, 4 is gonna be very small data value, so we are gonna disregard the 4 part, and we can find area less than this z value, the less than 1 area. So when you look at on your z table, you can see that z is equal to 0.3413, which is 30. This area is over here 34.13%. And when you subtract it from 50, you will get this small area 15.87%. So this tells us that our risk of a type 2 error of when shifts to 995 millimeter is gonna be 15.87%. And we can say that beta is equal to, when you round 15.87 to 2 decimal, 0.16. Next part of the question is the power. How we calculate the power? We are calculating the power using the formula 1 minus beta. So 1 minus beta was 0.16, is gonna give us 84 for the power calculation.